out. There we go. So the reactor that we're looking at with the soybean oil production process today is this CSTR that's being shown here. And you can see that I've tried to take a little bit more time to emphasize what the jacket looks like compared to the actual reactor. And so the jacket is actually a little bit shorter than the whole reactor. You can kind of imagine putting a bucket inside of another bucket. You can't get that first bucket all the way down inside the second bucket. And so the steam that's running around the outside of the reactor doesn't actually go all the way up the reactor. And so I've noted that by the 40 centimeter mark. And then the actual liquid level inside of the tank itself is at 50 centimeters. And so we pump in some soybean oil and presumably we get some product coming out. Hopefully the product coming out is mostly ester, right? Hopefully it's mostly biodiesel, so that we can then use that biodiesel for something. By itself, if you just take soybean oil and turn it into biodiesel, that would be carbon neutral. But by the time you actually pay for the production process, you've probably generated a little bit of CO2. So the actual burning of the resulting biodiesel, yeah, that part is carbon neutral. But the actual production of the fuel in the first place is probably not carbon neutral. That was actually one of the arguments against, oh boy, I'm going to date myself now, but like late 90s or so, there was this big push for ethanol from corn. And if you go back and do like the equilibrium analysis for production of bioethanol from corn, you don't even break even initially. You know, just from the production process, you lose so much in the bioproduction of ethanol or bioethanol production from corn that it's not really a net gain for CO2 emissions by the time you're done with it. You need so much energy in order to do primarily the separations. But at any rate, that is an aside that I don't think we're going to talk about. We've got a problem statement here. So we're just feeding some pure soybean oil, which actually a very similar process would happen if you wanted to use like waste oil from a restaurant or something like that. The general idea would be the same. You would provide the oil, you would provide the alcohol. So we're using methanol here. Methanol is really dangerous. I mean, if it gets on your skin or something like that, it's not like the end of the world, but if it somehow gets into your bloodstream. So if you eat it or you breathe in the vapors or something like that, and it's not, don't think like people just sit around eating methanol, although it has happened. That was one of the big reasons bootlegging was such a problem, was they couldn't get methanol out, or they would deliberately put it in there. It'll cause blindness very easily. So we're feeding that at a particular rate as well. And we just want to know a straightforward estimate the outlet composition and the reactor temperature for each of the following cases. So we're going to try to get through as many of the cases as we can. My guess is we'll get through case 1 and probably most of case 2. And then I might leave case 3 as either something that you can try for yourself, or I might just throw it onto the homework for next week. So don't forget that the first project is due later this week. And for that reason, the third homework will probably have fewer problems than normal. So it'll probably only have 3 or 4 problems on it, because I suspect a fair amount of your time will be spent on the project portion. So that's where we're at. We're going to take a look at case 1. I guess another point to bring up is I'm going to focus more on the setup of the problem. So when it comes time to actually put this into MATLAB, I guess I would not encourage you to try to type as fast as I'm going to type in MATLAB, because I'm going to be copy pasting pieces of code in there to focus more on the structure of the way that we assemble the MATLAB code rather than risk me actually typing and making another typo. We can speed it up a little bit that way. So we'll focus on setup and then analyzing the elements of the code and how they're assembled. Less so actually doing the coding right now. And then any code that we get to, I will post afterwards. So you'll have access to that as well. So let's switch back over to our notes, and we're going to go ahead and set up the first part, right? Isothermal operation. In other words, what would we get if we didn't have the jacket on there, right? If it was, or we didn't care what the jacket was doing, we only cared that it was making the system behave as though it was isothermal. A good place to get started with something like this is the table of wonder, right? Or the stoichiometric table. always a good place to get started. I will note, let's actually put the reaction components in here. So let me take a quick screenshot of this and throw it in there. There's our reactions. So there's actually 6 components in here, even though the reaction above, the overall reaction only shows 4, right? The overall shows soybean oil, alcohol, glycerol, and biodiesel. But there are these intermediates, the D here and the soybean oil, triglyceride. Here it is. That one. Soybean oil, diglyceride, monoglyceride. Yep. E is our ester. There we go. So there's these other 2 that are on here, diglyceride and a monoglyceride, which are intermediates that exist when you take a chunk of this and break it off. If you break one off, then you're left with 2 on the original backbone, here and here. And then if you break off another one, you're left with 1 on the backbone. And then finally you end up breaking that very last one off of the backbone in order to get the glycerol product coming over here. So we have that. Oops, let's not do that. There we go. A great way to summarize this is actually, like I said a moment ago, with the magic table, the stoichiometric table, table of wonder, whatever you want to call it. And so that's where we're going to start with this particular problem. And we're just going to draw it right next to this one. It's really helpful because one of the problems with a multi-reaction system is how do I keep track of all of the net rates? And the table of wonder makes that pretty easy because we can take an approach very similar to what we would have done back in 100. So we summarize the 3 stoichiometric coefficients, right? Stoichiometric coefficients for each species on reactions 1, 2, and 3. So our species will go let's keep it in the order that we've got here. S, diglyceride, mono, ester, glycerol, and alcohol. I only remember those because it kind of spells out SD mega, and that's the only reason I remember which one is which. So we can fill out these stoichiometric coefficients just from looking at our reaction. And so if we look at the soybean oil only participates in the first reaction, and then it's not in the second reaction, and it's not in the third reaction. And so as we would be accustomed to do, we would see -1, 0, and 0 for that. And we can go right on down the list, and we'll see a couple of different patterns that we have on here. If we look at the diglyceride shows up in reaction 1 as a product, but gets consumed in reaction 2 as a reactant. So this one would be a 1, a -1, and a 0. The monoglyceride is a product here and a reactant over here. So it would be a 0, a 1, and a -1. If I make a mistake along here, please correct me. Ester, the thing that we want, the E, shows up as a product in every one of them. So it gets a +1. The glycerol only shows up as a result of the third reaction. So we get a 1, a 0, 0, and a 1. And our alcohol gets consumed in every reaction. So we have -1, -1, and -1. The initial moles coming in are given to us in the problem statement, so we don't have to search very hard for that. We have 0.019 for the soybean oil, and we've got a lot of methanol, 205, a lot compared to the soybean oil. And then everything else is 0. The nice thing about the stoichiometric table, or this magic table that we've got here, I'm actually going to get rid of the thing up at the top so that we can use that space. There we go. The nice thing about this is that our material balance is usually written as this, R sub I V. So this is read as 0 is equal to out minus in minus change. But we can rearrange that. This is eventually how we need to solve it, right? We have more than one reaction. We have a lot of components involved here. When we put it into MATLAB, it's going to have to be written this way because that's how MATLAB will end up solving it, but you can actually use the stoichiometric table and make it look fairly similar to the way that you would have seen it before, which is this, right? Which is that the out is equal to the in plus the change. It's just previously, when you had seen something like this would have been written as the sum of the stoichiometric coefficients times the extensive reaction over all of the reaction. That still holds. We just don't write it that way anymore because we now have to make use of our rate laws. And there's not the material balance as we use it in equation 4.1 is the form that we need if we want to use rate laws. So we just don't include this part anymore. But if we want to write up our stoichiometric table just to keep an eye on how the net rates are used, we can do so like this, right? Where we just have to now remember that the R sub I looks like the sum of the stoichiometric coefficients in each reaction times the rate of reaction, R sub J. And so that can actually produce fairly neat looking equations such as N sub S, if we want to know how much of the soybean oil is coming out, that's equal to however much was coming in, 0.19, plus the net rate of soybean oil. Well, the net rate of soybean oil is each of these stoichiometric coefficients, so this one, and this one, times the rate for this reaction, or this reaction, right? Depending on which one you're looking at. So what we notice from this one is that it'll be minus R1 plus 0 plus 0, right? Because there is no, the soybean oil is not involved in any of the reactions except the first one. And similarly, the outlet molar flow rate of the diglyceride, there's none of it going in. So this ends up just looking like R1 minus R2 plus 0 times the volume. And so I'm in the habit of actually leaving those zeros in there, like this 0 and this 0 and this 0. I'm in the habit of leaving those in there for a little while. Maybe I don't need it later, but it just reminds me that I have presumably checked every one of these reactions to find out whether or not that species is involved. And so I don't have to say, if I come back and troubleshoot later, I don't have to ask myself, well, did I even look at the third reaction? At least I did that. And so I leave those zeros in there. Similarly for the monoglyceride, it's not involved in the first one. It's plus R2 and it's minus R3. All of that times the volume of our reactor. For the ester, which again is our product, that is our biodiesel, it's R1 plus R2 plus R3 times V. And then our glycerol, which is it is indeed a byproduct, but it's a pretty useful byproduct. And so 0, 0, and R3 times V. And then the moles of A being our alcohol. This one gets consumed. So we start off with 0.205 and then minus R1 minus R2 minus R3 times V. Got to kind of squeeze that in there. And you might notice this looks a little bit strange, right? You may not write it as a plus here and then a minus, and a minus. That's just a habit that I'm into because I'm usually pretty bad at tracking my signs down. It's easy. I have noticed that for me personally, I tend to make a lot of sign mistakes. And so I try to leave the signs there as long as I can. But that's just an error that I tend to make is something like that. So now it becomes a question of, well, in every one of these, I have an R, right? I need to know R1 for this one, R1, R2, R2, R3. So I need to have expressions for each one of those. Those are implied because we were told that these reactions are elementary. And so in the rate that's given here, we have a forwards rate constant and a reverse rate constant. And so we can write up our rates fairly quickly by reading those. If they're elementary and we focus on the first reaction, R1, remember it's going to be a forwards rate constant times the product of the concentrations of the reactants raised to their stoichiometric coefficients, which is a bit of a mouthful, but it's pretty easy to write for this one. It's C sub S times C sub A, right? Because we've got an S as a reactant and an A as a reactant, and their stoichiometric coefficients are 1 and 1. So it's just that. And then the reverse reaction is minus K sub R times C sub D, C sub E. Because on the reverse reaction, it's a D and an E with a stoichiometric coefficient of 1 and 1, but it's going in the opposite direction. This is what we would normally write as something like K sub F times C sub S, C sub A, minus C sub D, C sub E over capital K sub C, right? Those are equivalent, where K sub C is equal to, I want to say it's the forwards over the reverse, little kf over little k reverse. That's perfectly okay, right? If we could go look up, say, for example, the Gibbs energies of formations of soybean oil, alcohol, diglyceride, and the ester, the biodiesel, we could continue to use this form that we've seen before. The problem is we can't find that information very often. And so the easier way is for somebody to just go out and measure the forwards and the reverse constant on this particular problem. That tends not to be the case unless you've got usually biomolecules, right? Very, very large molecules can be very difficult to measure their thermodynamic quantities. And so sometimes you will see the rates written this way. So that would be okay in a different case if, for example, we had the ability to do the stuff we've done from chapter 2 where we can do the equilibrium stuff. But in this particular case, the reference that I'm using here, it just gave us the forwards and reverse. And so we don't, actually, let me leave that there. So we don't write it like the way that I've bracketed it in blue. We write it the way that I've written it to the left of the bracket. Oops. So our second rate, this is forwards 1, reverse 1. The forwards rate constant of reaction 2 times the concentration of D, which is our diglyceride and our alcohol. You might be right, I usually very frequently forget this form, but if I plug that in there, the KF, I think that's correct the way that I've got it because the KFs will cancel, but you could be right. I'm not accustomed to writing it that way, so I don't do that math a lot. So minus KR2, C sub M, C sub E. And finally, R sub 3 is K sub F3, C sub M, C sub A, minus KR3, C sub G, there we go, C sub G, C sub E. Right, and so each one of these rates, right, this R1, the rate of reaction 1 shows up inside of our net rates in a lot of places, right? Exactly that expression shows up for the soybean oil, the diglyceride, the ester, and the alcohol, right? So that one equation is going to get thrown away or thrown into a lot of different things. Same idea with 2 and 3. They're going to show up in a lot of different places. A nice thing about writing it this particular way is you don't have to do the algebra of substituting these all in there. I mean, eventually you have to do that, but in my case, we're going to let MATLAB do that for us. But we've kind of accomplished almost all of the engineering right here, right? We have set up all of the material balances, right, for all 6 of the species. Those are up here. And we have set up all of the terms of the net rates. Because those were already summarized over here. We noticed that the net rates needed the individual rates of reaction, so that was our R1, our R2, and our R3. And the only remaining thing that we need to do is figure out how do we either get the coefficients, so things like KF1 and KR1, but those were given to us. So if you check the problem statement, they're just constants. So we don't have too much of a problem there. And we need to know how do we connect the moles, for example, the moles of the soybean oil to the molar concentration of soybean oil. Fortunately, we're dealing with a liquid phase system, so that conversion is fairly easy. So in each one of these, the concentration of any species I is always the molar flow rate of I divided by the outlet volumetric flow rate. So that's the lowercase v. Since this is a liquid, we can get away with the assumption that it's about the same as, or in this case, it's exactly the same that the outlet volumetric flow rate is the same as the inlet volumetric flow rate. We can actually check that assumption on this problem. We're not going to, but if you're bored, let's go ahead and say that you're bored. You can try to check the inlet volumetric flow rate versus the outlet volumetric flow rate if you assume volume additivity, because I gave you all of the densities in the problem statement. The problem with that is it's probably not going to look like it balances very well because you've got soybean oil and alcohol together. And soybean oil is this massive molecule, and you can kind of fit lots of alcohols if you're very clever, and nature is very clever. You can kind of fit all of those alcohols around there a little bit tighter than you might expect. And so I don't know if that check would be very good or not, but the liquid approximation here would be okay, because everything is indeed a liquid here. So every concentration that we've got will be equal to a molar flow rate divided by a volumetric flow rate. And so this suggests that we can use MATLAB. Let's change this to red. So we can have MATLAB solve for this one. Right, if we solve for the n sub i's directly, as opposed to the conversion of something. Conversion doesn't really work if you have multiple reactions, so we're not going to try to set anything up like that. If you have multiple reactions, you kind of have to solve for all of the molar flow rates, and part of the reason for that is it's extremely convenient. You actually do have to, because you can't use conversion, but it's extremely convenient because we will have what we can think of as direct access. MATLAB will know what those values are. And so it becomes very easy to calculate concentrations as simply one of these divided by another one. We do have to estimate what that value is, because that was given to us in the problem statement. Oh, I don't know if that was actually given to it. Let me check that problem statement again, just to make sure. So there's a little bit of a discrepancy here. I'm just going to leave it for now. The inlet volumetric flow rate, let's see, that's actually, that's kind of a lot. Yeah, let's go ahead and do it anyway. We'll get slightly different numbers from what I had calculated earlier. So the inlet volumetric flow rate for the soybean oil, we know we're providing it at 1 kilogram per minute. And if we looked up the density of the soybean oil, we would see that it was 1 liter for every 0.930 kilograms. And I'm going to convert all of the time over into seconds because I don't want to carry around the minutes everywhere. Everything else is already given in seconds, so it's a little bit easier here. So this particular value, if we were to evaluate that, would be 0.018 liters per second. But we've got some methanol coming in as well. So we're going to add that methanol to it as well. But the methanol is nice because we already know how much methanol is coming in as a volumetric flow rate, so we don't have to try to adjust that. It's coming in at 500 milliliters per minute, I think is the number that I had. Yeah, 500 milliliters per minute. 500 milliliters. Actually, let's convert that real quick. 0.5 liters per minute. And every 1 minute is 60 seconds. So this one, I'm going to have to pull up the MATLAB real quick because I didn't actually do this calculation. Let's see, 0.5 divided by 60 is 0.0083. That's good. It's not actually changing it that much. 0.0083. So our total is just the sum of these two, right? We're interested in the sum of the volumetric flow rates. And so that one, what is it, about 18 plus 8 to 26, so about 0.026 liters per second. That shouldn't change too many of my numbers. I actually calculated it with just the soybean oil because that was the bigger one, but I realized that could be enough methanol that would make a difference. So we should include the methanol to be correct. And so now we can ask ourselves before we switch over to MATLAB, do we have everything that we think we need? Most likely, right? The only remaining thing that we might need is the volume of the reactor, because if I go up to about here, I probably should not keep my chat window minimized just in case anybody wants to chat. So if we look at all of the components that we've got up here, we've now got all of the information we need on our rates, right? We've got forward and reverse rate constants, all the concentration, stuff like that. But we don't have our volume over here. But the volume was actually given to us in a sense because the geometry of the reactor was given to us. And so the volume of the reactor, remember I'm putting these caps on the V to remind us what is the difference between volume and volumetric flow rate. One's lowercase, one's uppercase. And so I'm putting those caps on there to try to remind us that it's uppercase. And so the volume of this will generally look like the cross-sectional area times the height of our cylinder. And so the cross-sectional area is 1/4 pi d squared, and the height, in this case, it's just height. So if we plug in some numbers there, pi, the diameter that we have is 50 centimeters. So we'd end up squaring that. And now we need to take the height of the liquid, right? The jacket doesn't come all the way up. We're just interested in the height of the liquid, which was 50 centimeters. And we would need to convert that over to liters as well, which a cubic centimeter is a milliliter. So we'd end up having to divide that by 1,000. I think the answer to that ended up being like 0.8, but it's over in the MATLAB. So this was sort of like the engineering portion, right? We have now set up all of our net rates, all of our material balances are set, all of our rate laws seem to be ready to go. And so it becomes a question of MATLAB solving for all of these NIs. And so this is the part where I would, if you can type really fast, try to keep up, but I'm gonna be copy pasting portions of code so that we can look more at the overall structure of the code's syntax rather than spending an extra 5 or 10 minutes actually typing out the code. So I'm gonna switch this over to MATLAB. Here's our MATLAB. It's not 0, we're not starting with 0. So we're going to use a script for everything because generally we use scripts for most of our solution procedures. And so what we're going to have to start off with is a guess for every single one of our ends, right? So the general starting point is, what do I think the outlet is going to be? Well, I think it's going to be close to what it probably was for the inlet. That's just a guess, right? It could be very far off of that, but usually a starting point of the inlet, it's not a bad place to get started. If the guess fails, that's okay. We can always go back and solve it. The syntax for fsolve is not going to look any different than it has for anything else. It doesn't matter that we're solving multiple equations for multiple unknowns. So the syntax for fsolve is still fsolve. You give it a function handle and you provide it its initial guess. The output to that then is whatever the solution happens to be, right? So at its most basic, that's going to be our syntax. We build the local function, which I think I've mentioned this a few times before. I always build the local function from backwards to forwards, right? From bottom to top, because I think it's a little bit easier for me to keep track of exactly what goes where. So in order to remind me what the general structure is, the molar flow rates are coming in this soybean oil followed by diglyceride, monoglyceride, ester, glycerol, and alcohol form, the SD mega there. And so I like to just give myself a little note here that says, don't forget that the things are coming in this particular form. I can then take my rate laws and turn them into the forms that I need for MATLAB by looking over at the table of wonder that I had a minute ago. So let's pull that up real quick, just to remind you what that looks like. Right, so if we look at this table of wonder over here, I'm gonna take each one of these expressions, each one of these material balances, and I need to enter them into MATLAB. The problem is, remember, though, I've written them in this form just to show you that, hey, that's a convenient way to write it because that's the way that we've seen before. But don't forget, when we put it in MATLAB, it has to be in root finding form. So it has to look like outlet minus whatever came in minus net rate times V. And so it will look slightly different just because we have to rearrange it to root finding form, simply because that's the way that all solvers work, right? It's not just MATLAB solver that does that, it's all of the solvers that do that. So for example, if I want the solution for the soybean oil, you can see here that I've written the inlet amount of soybean oil plus the net rate term, right? That looks exactly the way that I had it over in the table of wonder, times the volume. And then I just subtract off the other term, right? So now we've got it in our root finding form. Root finding form, by the way, doesn't matter. I could multiply all that by -1. It would be perfectly fine with that. So as long as you're consistent, if you move everything over to the right or you move everything over to the left, it's perfectly fine. You can do it in either form that you want. Similarly, for the diglyceride, I would have something like this, right? There's no diglyceride coming in, so there's no equivalent of 0.019. It's just the net rate times V, subtracting off whatever the amount going out happens to be. The rest of them all look very similar to that, right? They all look like net rate minus whatever's going out, net rate minus whatever's going out. This one happens to be in plus net rate minus whatever's going out, because remember the sixth element is our alcohol. And so that has a little bit of stuff going out. I'm in the habit of pre-allocating for something like this. You could probably leave the Y's that way, but I like to just remind myself that there's supposed to be an equal number of material balances as there are components coming in. And so I like to pre-allocate with a line like this one, where it just says, make sure that Y has the right elements and the right shape to it, but you don't always have to do that. And now I have to try to link the two, right? I've got my material balances down on the bottom. I've got the molar flow rates coming in. I need to add a bunch of code in between these two sections, right? The material balances are here. The inlet of the code is up here. I need to add all of the pieces that I need, that MATLAB needs, in order to connect the two. And so a good place to start for me is going backwards, right? I know I need the rates, right? These net rates say things like R1, R2, R1, 0, 0, or R1, R2, R3. I definitely need those. I can take those directly the way that I wrote them before over on the table of wonder and type them exactly that way in my MATLAB code. The reason that it's really nice to type them exactly the same way as they showed up in your work is because it becomes much easier to troubleshoot them, right? I don't try to do a lot of substitutions in here. I can look at this and pretty quickly check that that's the right thing. I see it's CS, CA, CD, CE, and it's K reverse of 1 and K forwards of 1. There's some other elements that I would need along the way, but those are the major elements, right? And they're written in such a way that I don't have to worry too much about messing them up and not being able to check with the way that I wrote them before. I need those forwards and reverse rate constants. So these were given to us as constants. So I could just write all of the K forwards and all of the K reverses as vectors. I also need my volumetric flow rates and my volume. So those are the two values that we wrote before. I need to update my V0 right there. Let me double check what we had. That's actually supposed to be 0.026. 0.026. And then here's our volume for our 50 centimeter tank. That's 50 centimeters tall. A centimeter times centimeter times centimeter is a milliliter. And there's 1,000 milliliters in every liter. So we divide that by 1,000. The only things that remain here are how do we get our concentrations? Every one of our concentrations, it's always equal to a molar flow rate divided by a volumetric flow rate. And so I can put those in here and say the concentration of soybean oil is molar flow rate of soybean oil divided by V0, right? This looks very tedious to write, but the advantage of it being very tedious is that you can check the pattern very easily and figure out if you've made a mistake compared to the way that you wrote it when you were sort of setting it up theoretically, right? So I can look quickly at the alcohol and say, do I have the right expression for the alcohol? Well, I know it's got to be the molar flow rate of alcohol divided by the volumetric flow rate. So at least I didn't mess that part up, right? It's very easy to troubleshoot that particular piece. I would have to double check to make sure, things like units and that still work. And now it just becomes a question of what are my NSs, my NDs, and things like that. Well, I already have those because those are inputs to the function. Right, and that I think is the part that can be a little bit confusing when you're writing a system up like this, is how come we know what these are? Well, we don't really know what they are. It's that they are the inputs to our function here, and we're going to guess a bunch of values of them, right? So the logic behind the fsolve is if I could just guess the right values of these, I would get the right answer coming out the other side. How do I know I got the right answer? Well, if I take those guesses and I feed them to my function, and I do all these calculations, and I end up with this y parameter down here has zeros everywhere, then I've solved it. If I didn't guess correctly, then I won't get all zeros everywhere, and I need to go back and do another guess. But that's the thing that fsolve is doing for us. It's just we have to get it started, right? So conceptually, when we run this function, we quote unquote have access. We know, quote unquote, know what those molar flow rates are, in the sense that we can use them to calculate things. We won't actually know what their solution value is until MATLAB goes through and solves everything. But within that local function, we know what their value is, or at least we have access to it, and we can calculate things based on it. And so we've kind of very quickly, because I was copy pasting, generated a lot of code. But the idea of this code is that it's supposed to be very easy to troubleshoot. It's supposed to be very easy to track down typos of not getting the right concentration in the right place, to a lesser extent, not getting the units correct. So I've commented a lot of the lines here having the correct units. And then the actual solution procedure doesn't take very long, right? It's 2 lines, which is pretty short. We'll add another one just so that we can see what everything is. And let's go ahead and run this. Hopefully everything will come out just fine. That's good, right? We ran this, we got our equation solved. It's always so wonderful when you set up a big problem and it just comes back, yeah, solved it, great. And now we can take a look at a little bit of what's happening. These are all of our molar flow rates coming out. And remember, what we want to create is a lot of ester, right? A lot of biodiesel, which if you think back to the way that we've got the structure here, that's the 4th element, right? So the outlet molar flow rate of the ester of our biodiesel is pretty high, right? Our inlet of biodiesel or of soybean oil is very low, right? It used to be around 0.02, 0.01, something like that. And now it's dropped considerably further than that, right? So we've consumed a lot of our soybean oil. We don't have a lot of unreacted diglyceride or monoglyceride, which is good. And then we've also made some glycerol. We have tons of alcohol left over, right? Plenty of methanol left over. And so if we were trying to optimize the system, maybe we would consider reducing the amount of alcohol to avoid having quite so much coming out, but that would also slow it down. So maybe it's not the best idea. So that's an example of how we can solve a fairly large system, right? There's 6 components there and 3 different reactions, both of which are reversible. So we have both a forwards and a reverse rate. But we've written it in such a way that the math that we've got inside MATLAB looks as close as possible to the way that we would actually write those expressions. There's a question in chat, how come there's an apostrophe after nsol in display? Just because I wanted them to come out horizontal. If you took the apostrophe off, oops, go page up. If you took the apostrophe off, then they just come out vertical, and it's just harder to read, right? It just pushes the stuff off of the screen, and I didn't want it to push off the screen, but you're perfectly fine without an apostrophe. So now let's look at what do we have to change in order to solve the adiabatic system. So the nice thing about the structure that we've got here is none of these material balances have to change. If we want to do the adiabatic system, there's only a handful of things that have to change. By the way, if you're copying down this code, don't stress, I'm going to get over to the other page for the notes, but I am going to post all of that code. So if you don't have it written down, that's okay, because it's all going to get posted, so you'll be able to see it shortly. But let's get to this adiabatic portion so that we can find out what kind of modifications we have to make. So in our adiabatic system, Changes for the adiabatic case, right? So this is part 2 of this. The first change is kind of tedious. It's going to take a little while to actually code up, but it's not terrible. All of the rate constant, all k sub I, have to become functions of temperature. They have to become functions of temperature because we were given activation energies for each one. And so if we use the Arrhenius expression, then we will get temperature forms for each one of these, which will look something like they're all given at 50 degrees C. So if we take that value at 50 degrees C and multiply it by the exponential of the activation energy over R, and then multiply it by the change in temperatures, reciprocal change in temperatures, we get expressions that look like this. And we have to write one of those for every single rate. So we're going to need 6 of those. If we're clever with MATLAB, we can get away with just writing 2 of them, which is kind of nice. The bigger change is that we must also solve for T, right? And so our T is going to primarily come from the energy balance. The energy balance is equation 4.2, which looks like 0 times the sum of whatever's coming in, C sub P I, T minus T naught. Remember, that term represents the energy that went into heating up the feed stream to the reactor temperature. Because on a non-isothermal system, the feed does not need to be the same temperature as the reaction or the reactor, plus V times the sum of R sub J delta H sub J minus Q minus work shaft. We get a freebie of work shaft, right? We're never worried about that. The system happens to be adiabatic, so we're not worried about this one either. Let's take a quick look at what are the things that we know. In this expression, we're good with inlet moles, right? That was given to us for everything. The heat capacities for everything are good to go. Those are summarized in the problem statement. We know the inlet temperature. It's still going to be 50 degrees C. It's okay that we don't know the actual temperature because that's the thing we're going to solve for. So it's okay. Those are all either constants or temperatures. If we look at the next term, right, this one, which represents how much energy is either being absorbed or released by the reaction, we're good with the volume, right? It's the same volume of the reactor that we're going to deal with. This particular term looks like R sub 1 times delta H1 plus R sub 2 delta H2 plus R sub 3 delta H3. If we expand it out in that particular form and look at what we know and what we don't know, we're good with all of the R's, right? The R1 and the R2 and the R3, those are exactly the same R1 and R2 and R3 that we had up here. So those are good to go. We don't have a problem with that. Each of the delta H's, though, we haven't calculated those yet. Those are our enthalpies of reaction, but we have to keep in mind these are the enthalpy of reaction at the reactor temperature. Right, so this delta H, and this delta H, those are the enthalpies of reaction at the reaction temperature, or at the reactor temperature. And so if you look at the energy balance section of the textbook, each delta H sub J is delta H reference for reaction J plus delta CP T minus TR. This delta H reference, maybe we were given that delta H reference, maybe we weren't. In this particular case, we weren't. So we can estimate this as the sum of the stoichiometric coefficients times the enthalpies of formation at circle. Isn't R a function of reaction temperature too? Yep, so each one of these are, there's a question in chat, aren't these R functions of temperature? Yep, the functionality of temperature for each of those R's is coming in from our Ks, right? Because we have to rewrite each of these Ks as functions of temperature. So the form is not changed. The part that changes is the Ks are function of temperature. So that will get included. When we write an expression like this, the reference temperature for all of these is always going to be 298 K, because that's where enthalpies of formation are written at. And therefore, our reference temperature over here will be 298 K, because that's where our enthalpies of reaction are written up. this term, the delta CP, just follows a simple definition of delta. It's actually delta CP sub J for each reaction J. Get my right color, is nu sub I times C sub pi. Right, and we know all of those terms, right? We know all of the stoichiometric coefficients of each parameter, and we know all of the heat capacities for each parameter. So we would put that into our MATLAB code, right? So we would add an extra line in our MATLAB code where we're solving for this particular value, right? We're going to write that equation inside of MATLAB. And so we're at 349. Obviously, we don't have enough time to do that. I will post the solutions for the adiabatic case. I'll have to think about the jacketed. I might turn that into a homework problem. If so, then you'll have a good idea of where the homework problem is going to go. Some approximate answers that you can try while you're waiting for me to post this, if you want to give it a shot. The amount of biodiesel that we're going to create will be around 0.01 to 0.02 moles per second. Quite a bit lower than what we had before. And the outlet temperature is actually going to be less than 0 degrees C. The reason being, it's an endothermic reaction. All of those are actually endothermic reactions. And so we're absorbing a lot of energy in order to make these reactions go. That energy comes from somewhere. It's actually coming from the enthalpy of the inlet stream because the system is adiabatic. It's adiabatic, which is very easily accomplished just by wrapping the thing in a bunch of insulation. So we can't draw in energy from the atmosphere. We don't have any jacketed stuff on it yet because we're just dealing with adiabatic. So the whole thing is actually cooling. And it gets so cold that it's actually a problem because things will freeze. But that's as far as we got. So we're up to 350. Again, I will post the coded solutions for this adiabatic one as well. I'll think about the jacketed one, or I might just throw it onto the next homework. Since we're only going to have 3 or 4, that would be a good one to put on there. Don't forget the project is going to be due soon, and the quiz from last week's review is also due sometime today. So as always, I'll stick around and chat for a little while and answer any questions that you might have. We'll throw a little bit of the waiting room music on since it's terrible to sit here in dead silence. And then I will see you guys on Wednesday. Stay safe out there. Let's get a little bit of music here. So there's a question in chat. Where did the moles in the MATLAB file come from? Good question. Let's pull up that MATLAB file. Where are you at, MATLAB? There you are. The moles that are in the MATLAB file are given here, here, and here. And so that's the point that I had brought up earlier, which is kind of tricky, right? How come we know those moles? We don't actually know them. What we do know is that we have access to calculate things with their values. And the reason for that is because of how the fsolve function works, right? The fsolve function takes our initial guess, stuffs them into this function as an input, right? That's the key part, is the moles are coming into that function as an input. And so we can calculate things based on that input. In fact, we have to. Excuse me just a second. Dry throat. We can calculate things based on those inlets. And so that's why we can write them the way that we have here on lines 8 through 13, is because they're already there as an inlet. How do we know if we've guessed it correctly? That's what fsolve is doing, right? fsolve is trying a lot of different guesses until the guesses that it eventually provides as n satisfy these equations, right? Whatever values of n we put in end up giving y of a bunch of zeros. That's why we can use n in our MATLAB code. In the MATLAB code, can you clarify what you meant when you said that all of the y elements are 0? They're not. So this is an optional statement. It's just for me to make sure that I put enough elements into MATLAB, into the vector in order to start it. So if we enter the debugger and run this, let's pause the here and here. So right now we're inside the debugger and y does not exist, right? If I look over here in my workspace, there's no value of y. I am in the habit of not constructing vectors one at a time. I would rather have the whole vector and then just put elements into the vector. So if I go ahead and tell MATLAB to step through this first command, I will create y with a bunch of zeros, right? Y over here has a bunch of zeros. And if you continue to step through the commands, this is what MATLAB is actually doing. When it goes to calculate and look at the values inside y, I see I've got minus 29, 29, 0, 29, 0, and minus 29. By the time that I have actually solved this thing, I know all of these end up having to be equal to 0 because those are our material balances, right? We wrote them in root finding form, which is where those zeros come from. It just so happens that we don't often see what it's doing inside of there because MATLAB is the thing that's checking whether or not those are 0. But we can double check if we add another line up here. If we say display my function of nsol, right? If we actually push the solution back inside of the function and run it again, we should get things that are very, very close to 0 when they come out the other side. So remember, here was our solution value. We made a bunch of biodiesel, left over some alcohol, and we have some glycerol coming out. If we take these values and put them back inside my function, we should get numbers very, very close to 0. And indeed we do, right? We get things that are like close to machine precision, right? 10 to the minus 15, that's a decimal followed by 15 zeros. It's basically 0 everywhere, which means we have just satisfied the material balances to a very high degree of precision. Well, we haven't, FSolve has. So that's what I mean by these values, all of the y's end up having to be zeros. The path to get from our initial guess to our actual value, that's handled by FSolve, right? All of the guessing and stuff like that. For question 2 in the homework, is it valid to find the concentration by dividing density by molar mass? Yes. In fact, that's its definition. So yes, you can divide density by molar mass and you will get yourself a molar concentration. That's how you can estimate things like what's the molar concentration of pure water? Find the density of water divided by the molar mass of water. That's the molar concentration of pure water. How do we approach, actually, so there's 2 separate questions here. How do we approach 2.3 and how do we approach 2.6? So I'll open those up real quick. 2. Switch over to a different share. So the approach to 2.3 is to first draw the system and then do a material balance on A everywhere. So on each unit that you have, you should draw it and do a material balance on A. What that looks like in practice. Let's add a little bit of room here. What does it look like to draw the whole system? That would look like we have our reactor. So this is our little CSTR. We have a separator going in afterwards. We take the outlet from the reactor. We make a little bit of product, but then we recycle some of it, right? So this was, I believe, pure A. If we, I think, label this as stream 3, 2, and 4 over here, pure A, we know that that's 60% of whatever came out. So the process spec for that means that the moles of A in stream 1 is 0.6 times the moles of A in stream 3, right? So there's a process spec that tells us how to go from stream 3 to stream 1 in terms of moles of A. If we combine these two, we just add the moles of A in stream 0 plus the moles of A in stream 1. Those end up equaling the moles of A in stream 2. And then our material balance on our reactor is out minus in minus R sub A times V, right? And so now we've got a system of equations and we need to solve them for N sub A in stream 3. This is actually, if we wanted to be specific with our nomenclature, it's N sub A 3 minus N sub A 2 minus R sub A times V. The other tricky part of 2.6 is that the volumetric flow rate of 2, so the volumetric flow rate in stream 2, let's just call it V sub 2, is equal to V sub 0 plus V sub 1. And then that is also equal to V sub 3. This is for liquids, right? So all of our liquids have added up. And so you'll have to, I believe you're given V sub 0, that hasn't changed. And then you'll have to express V sub 1, as somebody had just mentioned in the chat, as volumetric flow rate, which you can calculate by knowing this information over here, along with density and molar masses. So you might have to look up a molar mass. And then there's another question for problem 2.3. Oh, sorry. So to finish problem 2.3, set all of those equations up and solve them. I would try to get it down to just one equation, right? Try to solve just the material balance by substituting in these other terms until there's only one unknown in the material balance. That's how I would go about that one. In terms of the other homework problem, let's share that one. It was 2.6. How do we approach 2.6? Scroll down to 2.6. Oh, so 2.6, I would actually approach very similarly to the way that I just set up the adiabatic case. You'll just have fewer things to worry about, and then your Q term will actually exist. So comment this real quick. The thing that's different about 2.6 compared to what I just did, it's actually similar to what John did. It has a heat exchanger, right? And it's got this lumped parameter. And so you'll have to account for that in your energy balance. The way that you'll account for that in your energy balance will be through the Q term, which is this one. Not that, that's a D. Here. Right, so you now have a heat exchanger, and so you no longer have an adiabatic system. So the rest of the energy balance looks the same, except now you have Q. And so for homework problem 2.6, you'll have that Q is equal to UA times TU minus T. And that's what John had in his example the other day. What I have told you in this case is that UA is known. And so UA is given to you as, I think it was like 15 kilojoules per K, kilojoules per Celsius, 15 kilojoules per minute per Celsius. Kilojoules per minute per Celsius. So in that sense, it's got one less step than the one that John did on Friday, because you don't have to calculate the U or the A. You know what together they equal 15 kilojoules per mole per degree C. That is the lump parameter UA, and T sub U is known. It's a constant temperature. So you'll set this up in a very similar way. You might take a look at the code that I'll post for this example, for the adiabatic case from the in-class example, to get an idea of what that looks like. For the adiabatic case, if the end goal is to find T, how do we find the composition, or is it the same as the composition for the isothermal case? So the end result for this case will be that we have another element in Y, which is the solution for the energy balance. And so that means we need an additional input. And so if we look over at our MATLAB, what this ends up meaning is that we will down here have something like Y of 7 is equal to something, right? But this is the energy balance in root finding form. Because we have an additional element, we have another equation to solve, we also need another parameter that we can use to solve it. That last one is now going to be temperature, right? So our temperature will actually be the seventh input, and it'll probably be in units of Kelvin. And then up here, we would need an initial guess for temperature, which if it was the inlet temperature, would be 50 plus 273. And so now our temperature is actually something that we're solving for. It's an additional element inside of the code. naturally, you'll be able to look at this example to figure that out, but you can also, or not to figure it out, to see an example of how that works. When I post this code, you'll be able to see that. But we use almost exactly the same code in thermal, non-isothermal. Example 4.8 in your book. So 4.8 has another example of how can we set this up with the temperature as an additional parameter. And that one I think actually has the utility as an additional temperature too. But I've tried to go through that one and summarize very clearly in a table in there as best I can, where did all of these parameters come from and what equation did I use to find them, as well as a brief description of what they are. So 2.8 or 4.8 is a big example in your book. You might look at John's example from Friday first and this example second, and then go look at example 4.8, because 4.8 is a very general approach. You're welcome. For problem 2.3, how do we guess the moles of A going into the system from stream 0? Oh, for stream 0, in the way that I've drawn it, it's the same as the fresh feed from the previous case. Right, so if you draw it this way, this stream 0, that's your old fresh feed. That one. You're welcome. Rho over molar mass, generally that's just used for pure species, yeah. I mean, technically it can work, right? If you know the density of a mixture and you happen to know the molar mass of the mixture, the idea is the same. It's just rare that you can get an average density of a mixture. It's not something that's tabulated very often, and so we're often in a case where we take those two separately. And so, yeah, we basically just apply it for pure species, but the idea works for a mixture. If you happen to know, like it was an ethanol water mixture and you knew its density and you happen to know that its average molar mass was also something else, you could estimate the average molar concentration doing that. It's just we probably wouldn't do that. So yeah, it's basically for pure species. All right, I'm going to go ahead and stop recording this, start wrapping things up here. Stop recording.